Hi, in the last session, we explained the block diagram of UART receiver module and we explained the functioning of each module. Now, in this session, we will write the VHDL code for this shift register module. Now, before starting, let me quickly brief this shift register module, that what it will do and why we are designing this. So we are designing this shift register module because the data which we are receiving at the input of UART receiver is a serial data. Means data is coming one after one. So to retrieve our data, we need to capture all of these individual bits receiving at the receiver module, and we have to convert it into parallel data stream. So this shift register module will capture this serial data stream and convert it into the parallel data stream. So you can see we have this D in input and this is a serial data stream. And we have D out and this is a parallel data out. Now because we are using RS-232 protocol, so we need to capture input D in at every specific time frame, which we will define by the baud rate or a baud period. Means we will not capture D in all the time. Instead, we will use this shift enable input pulse to capture D in. Okay. So we will design a cascade set of a flip-flops, means output of one flip-flop will be connected to the input of next flip-flop. And when we will detect this shift enable pulse, we will capture this D in input. And also we will shift our existing data through the flip-flops. And in the last, we will capture all the bits from the output of each individual flip-flops so that we can get all the data bits together, right? Don't worry if this is not clear at the moment, because we are going to write the VHDL code for this and we will explain this once again, that how we are doing this. Okay, so let's move to the coding part. Okay, so first we will open Notepad++ and now we will create a new file. So click on this button. Now first we will save this file as .vhd or VHDL file. So click on file, then save as. Now go to our folder, so that is in UART project, and we have source folder inside it. So like previous, we will save all of our source file in this folder. Okay. Now give some name to this file. Let's give it shift register. So shift register. Now select the file type. So the file type is VHDL. So basic hardware description language. Now click on save. So first we will give the library and package declaration. So give it library IEEE use IEEE dot std underscore logic underscore 1164 dot all. Now this is the time for entity declaration. So give it entity. Now suppose our module name is shift register. So give it shift register is. Now first I will give the generic declaration and then port declaration. Okay. So first write the structure for it. So generic. Now in this section, we will define all of our generics, right? And next is port declaration. So give it port. Now bracket close, semicolon and entity. So this is the basic structure of our entity, right? Now first we will define our ports. So give it. So first I will define the standard inputs. So that is clock and reset. So give it clock. That is input type and std underscore logic. And we have reset, that is in std underscore logic. Now, if you look at the block diagram of UART receiver, then you will see that we have three ports inside this shift register. That is shift enable, that is input type. We have D in, that is again input type. And we have D out, that is output type. And also that is having the parallel data output. So define them one by one. So we have shift enable, that is input type and std underscore logic. We have D in, that is again input type and std underscore logic. Next we have D out. So that is output type and this is std logic vector. And now we have to define the range of this DO. So if you are working on the 8-bit data width, then this will be 7 down to 0, right? But instead hard coding this 7, we will prefer to use a generic because RS-232 protocol supports from 5-bit to up to 8 or 9 data bits, right? So I really don't want to hard code this value because if in some other application, if I want to change my data width, then I have to write this code once again. Okay, so instead hard coding this, I will use generic. And let's suppose the generic name is data width. So data width minus 1. Okay, so let's define this data width in the generic section here. So this is data width and that is integer type, right? Okay, so that's complete our entity part. Next is architecture. So first we will write the body of this architecture. So architecture behave of shift register is now begin and in the last and architecture, or you can write and architecture name. So this is behave. Now, because we are designing a shift register, and if you recall from our previous sessions where we have explained the shift register and their functioning and their physical structure, so there we have explained that shift register is actually a cascading of flip-flops. Means output of one flip-flop going to the input to the next flip-flop. Means all of the flip-flops are connected in the series. Output of one flip-flop going to the input of next flip-flop. So for this shift register, we have used registered process block. Okay, so we are doing the same thing here as well. So we will write a registered process block. Okay, so first we will give some name to this process. Suppose the process name is shift process. Now process, because this is a registered process block, so we will use clock and reset in the sensitivity list. So clock and reset are in the sensitivity list. Next begin and in the last and process. So this is the basic structure of process block. Now we will write the structure for a registered process block. So just write the framework for this registered process block first. So if reset is equals to 1, then do something. Else if at rising edge of clock, then do something and if. Let me correct the spelling of else if. So it is ELSIF. Now we will write the code for the shift register. Okay. Now we will use one internal signal for this shift register. And suppose this shift register name is SR. So when this reset is asserted, means when reset is high, then suppose our SR signal gets logical high at all of these elements. So SR gets the value of others 1 semicolon. Now first define this SR inside this architecture section. So this is a signal SR and that is std logic vector and having the same range as D out. So let's copy this and paste it here. So we have signal SR that is std logic vector and having the same range as our D out. And at this line, when reset is high, all of its elements gets a value logical high. Okay. Now what will happen when the rising edge of clock is detected? So when we have the rising edge of clock, we need to shift our data. Now the question is that where to shift the data, either towards the left or towards the right. Please note that we are designing a UART communication based on RS-232 protocol. And as I explained that RS-232 protocol sends the LSB first, means least significant bit first. So in this case, we will shift our data towards the right. Don't worry, I will explain it in some time in more details. But before this, we need to understand that we are not going to shift these flip-flop data at all the times when we detect this rising edge of clock, right? Instead, we will only shift our data when this shift enable pin is asserted, right? So let's write this logic first. So when this rising edge of clock is detected, then we will check this shift enable pin. So when this shift enable is equals to 1, then what will happen? We will shift our data towards the right. So our shift register will be D in concatenation with shift register. Now the leftmost value of shift register, so SR left down to 1 semicolon, right? And if. And that's it. Our shift register has been created. Now this is the most important line here in this program. So let me explain it. So what is happening that first we are looking for this rising edge of clock, and then we are detecting this shift enable pin. So at this condition, we will capture this D in at the MSB position. And then we shift the shift register data towards the right by one factor. So we have written SR left down to 1. This means that this D in input, which comes from the input ports from here, that will be captured at the MSB of this shift register. And the existing data of shift register moves towards the right. So the 0th index will be moved out from this shift register. So we have this statement. Okay. Now this is fine if you're working on the RS-232 protocol, where you are transferring the least significant bit first. But now suppose you are working on some other project where you are not using RS-232, and at that application you are about to transfer the MSB first. So the question is that how you are going to implement that. Pause this video and think a bit. Okay, so let me explain this, or even let me implement this in this code itself, so that we can use the same code on those applications as well. So what I'm going to do, that I will create a new generic here, which will tell us that either we are going to use MSB as a first bit or first transferring bit, or we are going to use LSB as first transferring bit. Okay, so let's give it some name. Let's mark it MSB or LSB. Okay, and that is character type. And now we are going to use if generate statement for this purpose, right? Okay, so first write the structure for this if generate statement. So first we will give some title name. So suppose this is LSB underscore first. Now write the generate statement. So if MSB or LSB is equals to L, then generate, and in the last and generate. Okay. Now, because this code here, that we have written it for the LSB first, right? So what I will do, that I will move this code inside this generate statement. Okay. So that's very simple. Let me correct the spell here. So that's and generate. Now I will copy this whole code because everything is going to same if I'm going to transfer the MSB first. So what will happen then, this MSB or LSB is M. Let's change its name. So that is MSB first. Everything is same. The only difference is shifting operation, right? Because now we are transferring the most significant bit first. So we need to shift our data towards the left by one factor. Okay, so that is very simple. Let's remove this D in from here. So we have this SR, that is SR left -1 down to 0 and concatenation with D in. So what will happen, that when this rising edge of clock is detected and we have this shift enable is asserted, then this D in input will be captured at the index 0 of this shift register, right? And all the elements of shift register will shift towards the left by one factor. And that's it. So when you specify that you are going to send the least significant bit first, then this line of code will be generated, or the structure from this code is generated. Or when you specify that you are going to transfer MSB first, then these line of codes will generate the structure, right? Now, one important thing, that everything that we have developed, that is on this shift register, and that is our internal signal. We have not done anything on this D output, right? So what I will do, that I will move the shift register data towards this D out. So this is D out gets the value of SR. So remember, all the structure of flip-flops will be generated on this shift register signal. And D out is just like the wiring up those shift register outputs to the output port, right? So if shift register is 8-bit wide, then all of 8 wires will be connected to the 8 wires of D out. Okay, so I think the code is done. So this is our library declaration. This is the entity declaration along with generic and port section. And next we have this architecture. Okay. Now let's save this program. So Control S. Now first we will compile this code for any syntax error, and then we will write a test bench for the shift register, and we will look for the output in the terms of waveforms, right? So for that we will open Model Sim Simulator. So open Model Sim. Okay, let's maximize this. Okay, so right click. Now click on Add to Project and select this existing file option. Now click on Browse. Now select the source folder from our project, and now you will see your shift register module here. So just select it and click on Open. Now click on OK. Now first we will compile this shift register program. So right click and click on Compile and Compile selected. So you can see that compile of shift register.vsd is successful and it does not have any syntax error. So this is the time to write a test bench for this shift register module. Okay, so that was our shift register module for UART receiver. Next, we are going to write test bench for this module and we will simulate it. So stay tuned for the updates and thank you for watching.